Assalamualaikum students. So today we are going to discuss a very important topic in thermodynamics, which is known as the Carnot cycle. So it is very important to know about this life-changing cycle given by Sadi Carnot, who was a French physicist. That this cycle basically provided a model for the practical auto and diesel engines. It is an ideal heat engine cycle which is composed of four reversible processes, and it uses ideal gas as a working substance. So it is a perfect engine which assumes that there is no friction between the piston and the walls of the cylinder, and the walls of the cylinders are insulating, that no heat can enter or leave from these walls. The only heat which can enter or leave in these systems is from the base of these cylinders. So how this cycle works basically, uh, thus the simplest possible engine basically works in conjunction with a heat source which is at temperature T1 and a heat sink which is at temperature T2. So in one cycle, the heat source transfers energy Q1 to the engine, which does some useful work W, and transfers extra heat Q2 to the heat sink. So at the end of one cycle or each cycle, the energy and entropy of the engines are unchanged because they return to their original state. So the reversible engine of this type is known as a Carnot engine. So now let's discuss about the four reversible processes in this cycle. The first one is known as the isothermal expansion. The second one is the adiabatic expansion. The third one is the isothermal compression, and the last one is the adiabatic compression. That is in first cycle, that is the isothermal expansion. The gas is allowed to expand isothermally. That is the temperature of this gas remain constant. And the pressure and volume adjust themselves in such a way that the temperature remain constant. So if we plot this um, isothermal expansion process in a PV diagram, you will have an isotherm which is given by this AB curve. Similarly, during the second cycle, that is the adiabatic expansion, your system is present at pressure P2, volume V2, and temperature T1. So, from this these parameters, since there is an adiabatic expansion, no heat can enter or leave the system. It means that whenever there is an expansion in the system, this will result in decrease in temperature of this system. If you plot a curve for this process in the PV diagram, this will be given by this BC curve, which is known as an adiabat. And remember that this adiabat is more steeper than this isotherm, because the expression for the PV in case of the adiabatic process is PV gamma is equals to constant. So the third process is the isothermal compression. That is, the gas is allowed to compress isothermally, keeping the temperature of the gas constant. So it means that it started with temperature T2, it will end with temperature T2. And again, similarly, definitely the pressure and volume will adjust themselves to keep the temperature same. So it means that it is again an isothermal process, and which is shown here. It means that since the gas is compressed isothermally, it means that it will uh, reject the extra heat to the heat sink. So the last process is basically the adiabatic compression. That is, no heat can enter or leave the system. So if the gas is compressed adiabatically, this will give rise to increase in temperature of the system. And so this is the last step. It means that the initial temperature of the system will be achieved, which is the temperature T1. So uh, we are interested here to find out the efficiency of such a heat engine. And efficiency of a heat engine is defined as the what you gain from your engine, and divided by what you spend on that engine, that how much energy you spend on that engine and how much work the engine provided in return. So that's the efficiency, and we are going to calculate this efficiency for this Carnot cycle. So let's find out the work done during the first process from A to B, that is during an isothermal expansion. And we know that the work is defined as minus PdV. So we will integrate here from some initial volume VA to some final volume VB. And since we are using an ideal gas in this engine, so for an ideal gas, we know the equation of state is given by PV is equals to NKB T1, or we can write it as PV is equals to N times Na kBT, where we know that Na times Kb is equals to the gas constant R. So it means that this ideal gas equation can also be written as PV is equals to nRT, where R is the gas constant, which is equals to 8.31. So putting the value of pressure in terms of volume, we will have uh, nkb T1 divided by V into dV, and the nkb times T1 is constant, which can be taken out of this integral. So you will have a minus sign is there as well. So minus nkb T1 into dV over V into integral of VA to VB. So the integration of this integrand will be equal to log of V, and after putting these limits, you will have log of VB over VA. So the work done during an isothermal expansion will be equal to minus NKB T1 log of VB over VA. And from the first law of thermodynamics, we'll have delta U is equals to delta Q plus delta W. And since this is an isothermal expansion, there is no change in temperature. So it means that delta U is equals to 0. So delta Q will be equal to minus delta W. And delta Q in this case is the heat added, which is the heat which is added in this system, and which is Q1 in this case. So the Q1 will be equals to minus delta W, and delta W is equals to NKB T1 log of VB over VA. So negative negative will give you positive sign. So Q1 will be equal to NKB T1 log of VB over VA. So this is the work done during an isothermal expansion, and this is the heat which is added to this system. So similarly, the third step is also an isothermal compression. So it means that the work done for an isothermal process, isothermal compression, can also be find out by doing this similar calculation. And the work done for this from C to D, that is from for isothermal compression, will be equal to N kb T2 log of Vd over Vc. So now we are going to find out the work done during an adiabatic expansion, and that is for the cycle B to C. And in this case, in adiabatic expansion, we know that in adiabatic process, no heat can enter or leave the system. So the first law of thermodynamics will give you delta U is equals to delta W, or delta W is equal to delta U. And since we said that we are using an ideal gas as working substance, and from the kinetic theory of gases, we know that the internal energy of a monatomic gas is equals to 3 by 2 nkbt. So it means that in this case, the change in internal energy of this ideal gas will be equal to 3 by 2 nkb delta T, and delta Tv is the change in temperature. Since it is an isothermal expansion, it means that the final temperature will be less than that of the initial temperature. So putting the value of delta T, you will have delta U or delta W equal to NKB T2 minus T1. And similarly, we can find out the work done in an adiabatic during an adiabatic compression, that is from D to A, which will equal to delta U equals to 3 by 2 nkb delta T is equals to 3 by 2 nkb T1 minus T2. So it means that in this case, the work done will be equal to 3 by 2 nkb T1 minus T2. So this is an adiabatic compression. It means that the final temperature will be higher in this case. So this difference will be equal to T1 minus T2. So the total work done in going from A to B, B to C, C to D, and again coming back to D to A will be equal to the work done from A to B plus the work done from B to C, the work done along C to D, and the work done from D to A. So putting the values which we have already calculated along these paths, we will have this equation, and we can find out that the second and third term are the same, but with the opposite sign. That is, you can take a negative sign common from this. It means that this second and third term will cancel, and you will have you are left with minus nkbt1 log of vb over va minus nkbt2 log of vd over vc, and from here you can take nkb common, and you will have t1 log of vb over va minus t2 log of plus t2 log of vd over vc within this bracket. So this is the net work done during this process, during this cycle. So we are now in position to find out the efficiency for this Carnot cycle, which is defined as the what you gain and what you spend. What you gain is the work that you extracted from this cycle, and what you spend was the energy that you initially provided to this system. So this efficiency will be equal to the net work done divided by IQ1, and the net work done is equal to this equation. So putting this value of this net work done here and dividing it by Q1, which is equals to nkbt1 log of VB over VA. So after doing a little bit calculation, you will find that that efficiency will be equal to 1 plus T2 over T1 log of VD over VC divided by log of VB over VA. So this can be solved further by considering the adiabatic processes. We know that in an adiabatic process, the product of P times V is equals to constant, or you can also write, you also know that the product of T times V power gamma minus 1 is equals to constant, where gamma is the ratio of specific heat at constant volume to the specific heat at constant pressure to the specific heat at constant volume. So I will give these expressions. I will leave these expressions to you to find out for the adiabatic processes. So we know that the adiabatic process is involved from B to C and D to A. So it means that this equation can be used for adiabatic processes. So from for B to C cycle, you will have T1 VB power gamma minus 1 is equal to T2 VC power gamma minus 1. And similarly for D to A, you will have T2 VD gamma minus 1 equal to T1 VA gamma minus 1. So solving above these two equations, we can write VB over VA is equals to VC over VD power gamma minus 1. So it means that you can put this inequality in here, and you will find that the efficiency will be equal to 1 plus T2 over T1 log of VD over VC divided by log of VC over VD. So you can change uh, uh, this term in this bracket, that you can also write it as a minus log of VD over VC. So that minus will be taken here. So it means that the efficiency of this cycle will be equal to 1 minus T2 over T1 log of uh, VB over VA or log of VB over VA. So you can also write in this way. So it means that this term will cancel out with each other, and you will have 1 minus T2 over T1. So what we find here is that you can write uh, this expression uh, in terms of VC and VD as well as in terms of VB and VA. So the final efficiency of this cycle will be equal to 1 minus T2 over T1, and this shows that the efficiency of this Carnot cycle can't be 100%. So it is always less than 1, and it depends on the temperatures of heat sink and heat source, and it is independent of the gas you are using, the working substance. So again, you have a heat source which is at temperature T2, from which you are getting some energy Q1, which you are giving to this engine, and this engine does some useful work and injects extra heat to the heat sink. So this is the um, main, uh, um, I mean, way the way the how this Carnot cycle is working. And from this engine you can find out that this q1 is equal to the work which is being done and the extra energy which is being released here. So it means that q1 equals to q2 plus w, or w is equals to q1 minus q2. So efficiency can also be written in terms of q1 and q2, which will be equal to w over q1, and w is equals to q1 minus q2 divided by q1, which is equals to 1 minus q2 over q1. So you can also write the efficiency in terms of temperatures, but also in terms of the heat uh, given and rejected by the system. So this is the most efficient engine in thermodynamics, and it is a perfect engine which is based on four reversible processes, and the thermal capacities of both the heat source and the heat sinks in this case is infinite. So again, I will say that this is the most important cycle which changed our life because it provided a model for the most practical engines, that is the auto and diesel cycles. So that's it for today's lecture. In coming lectures, we will discuss about the cycles which these practical engines follow. That is we will study about the auto cycle and the diesel cycle. Thank you.